So, my name is Wijnand Schoenmakers, and I'm a senior engineer at Flow Research Group. I'll be giving you an introduction of BOSpulse, the new software release. First, a little bit of an introduction about BOSpulse in general. It's a pulsation software package, and the main focus is on reciprocating pump and compressor analysis. I see it should be the other way around, but you can also study general pulsation phenomena with this package. So DRG is a little bit about who we are as DRG. We are an engineering consultancy firm, and we have three main activities. We build it up with our engineering consultancy, which is regarding the pulsation and vibration analysis we do. We use our own software as well, but it's also a little bit broader that we do FEA analysis and CFD analysis, anything regarding piping, pressure vessels, both mechanical and fluid dynamics. Second, we develop our own software. So BOSpulse is one of our software packages. BOSfluids is a similar package focused on surge analysis. And then we also have some other FEA packages which we resell. And then finally, we also offer training courses. We have an upcoming Flow conference as well. And we provide training courses in our own software packages, in some other software packages, including Caesar 2, for example, and in general engineering topics. So a little bit more about our engineering consultancy. You can see we have different types of services, how we like to group it. Some pressure, thermal equipment, mostly regarding fatigue analysis. We have some fiberglass piping, which we do a lot of. So fiberglass stress analysis, it's a little bit different type of analysis regarding different from steel analysis because it's an isotropic material. So we're very familiar with those type of analysis. We also do gas, LNG, compressors and pumps. So this is also where the pulsation and vibration analysis comes into play, as well as BOSpulse, the software package. And then we perform most of the time pulsation and mechanical response studies. We have some flow analysis, some flow assurance, surge analysis, and we also couple those sometimes with mechanical analysis as well. And then finally, we have some software consulting. So now let's go into our new BOSpulse release. Well, I sort of tried to make a list of some key elements. So initially, BOSpulse is very intuitive in how to model and set up things. I'll go through this list, and then later on I will take you through the program and highlight all those features, how they are built into the program. And you can also see how a model is built up. So we have tinkered a little bit with the model setup, improved sort of the workflow. Then BOSpulse also has a good interface with other packages. So we use it a lot for pulsation analysis, and then we couple it with Caesar 2 piping stress analysis package to use the shaking forces as an input for a mechanical study. And as I'll show you later on, it's a very straightforward and easy flow going from BOSpulse to Caesar 2, and even the other way around. A new feature what we added is importing piping component files. So most CAD programs can create a PCF file, and we can use that to create a model. For pulsation analysis, we have not used it that much, but especially for surge analysis, very large systems, I believe even it sounds to me almost unbelievable, 1,000 isometrics we have imported and created a model from. So that really helped our workflow in setting up a model. And then also another importing feature is the pipe profile. This is just a comma separated file. And you can just give the coordinates of the different elements, and then it will read that in. It's especially designed for pipe profiles. So, for example, 2D, where you just want to see the height differences versus length. Another thing that BOSpulse is, well, one of the key elements of BOSpulse is the saving time during analysis and design. This also came into play because we use it a lot. And so we're continuously improving our workflow. So you can run multiple simulations in parallel. So if you have a multi-core laptop or a computer, most people have these days, you can run multiple simulations. So that saves a lot of time. We've created a new solver. So I'll highlight that as well. That's a new feature of this new release. It's especially designed for pulsation analysis, and as I will show you, it's really a really fast solver in some systems, and it can save you a large amount of time, especially for design purposes where you need to iterate through your system a lot. And then also we improved the code evaluation of the API 6.18 and the API 6.7.4. Especially regarding the 6.18, we've added additional automatic checks of the pressure suppression devices and the pressures at the compressor flange. And then finally, we also added the customizable report, pulsation analysis. The results of the analysis is a large amount of data, and this customizable report allows you to sort of filter out the most important data. And because it's customizable, you can sort of give it your own flavor in what, specifically on what type you're interested in. So that was a little bit about the presentation, and now I'll just jump straight into BOSpulse itself. So here you can see a typical starting screen for your new BOSpulse model. There are no elements inside yet. And you can just simply create a new element. It's very similar to Seizure 2. So for example, you give it some length. So this is a pipe element, and we'll give it some diameter, 10 inch. This is similar to Seizure 2, where it automatically looks up the schedule and the size. We give it the standard schedule. And there we have our first. So modeling is very similar to Seizure 2, where well, it's an easy workflow. But I want to highlight especially a new feature, and that's the importing the PCF files. So that's what I will show now. Is I'll go to import. I'll select. So I have multiple isometrics here. I'll select. I'll just have to select one, and it will automatically import all the other ones. I will place the model, so it will throw out that one element that there was there. Here are some settings, which I will just leave to default for now. And as soon as I do that, it gives me some warnings because I didn't specify the pipe schedule and stuff like that. And here is our model. So it's all connected. There are a lot of tricks in the PCF importer, or tricks, a lot of processing being done in trying to match the different PCF files together. Also, because most of the time the isometrics are not exact when they're being exported. Sometimes there's a little bit of a mismatch between the different files, and there's an algorithm that will detect that and try to fix it as best as possible. Especially if you have 1,000 isometrics, you really want software to take care of the little errors and automatically create a good model. So finally, before we continue setting up our model, I'll just merge all the elements. Right now, there are some little elements in between. As you can see here, that's the boundary maybe of a isometric. Merge those. It's really simple in BOSpulse, and now they're all straight pipe. So now this is the discharge of a compressor system. There's a cooler bank here. It's already modeled, and the only thing we need to model is, for example, the pulsation bottle itself. Now I'll do it a little bit simplistic. Maybe not completely realistic, but it will illustrate a little bit of how to model. So we'll go to piping, add a new element. And we'll just give it a diameter of 20 inch. We'll change the length to 100. This is something that could be a pulsation bubble. And then we'll just add a compressor, for example. be a single piston. This would be the compressor passageway. Then we'll add two different, the head end and the crank end. So this is something that could be the compressor cylinder. One end is the head end, one end is the crank end, and now we can set up those conditions. So one of the features is that you can actually add a reciprocating compressor boundary condition, and all you need to do is fill out these fields. These are typical, or these are known parameters for a reciprocating compressor, and we'll automatically use that to determine the correct flow rate profile. That's going to be the input of our model, and you do not need to create that yourself. It's now the only difference is that we had a head end and a crank end. So right now the phase shift is 0, so they fire at the same moment. So all we need to do is say this is the crank end at a phase shift of 180. Then we can correct a little bit of the piston area because there's a conduit sticking through that end. Not really any new features, but just for setting up the model. The final thing we need to do is to set up the analysis. It's a compressor system, so we'll do an API 618. It asks you at what frequency do you want to analyze it. We'll do it at 5 Hz for now, and we'll use. And then we'll say what kind of gas it is. This is still all unchanged. Now we can go to the interesting part, because there's a new button here called solution method. It says transient or harmonic. And the harmonic solver is the special designed fast solver. So we'll just copy a case twice, and I'm going to illustrate the effect. So for the harmonic, we have one case that's called harmonic. We'll use the harmonic solver. And we have one case that's the transient, and that one includes the transient solver. And then we'll just execute them. So one thing to set a pressure boundary condition. So this system goes, as a discharge goes through a cooler, and maybe it goes to a vessel here at a fixed pressure. Now we can run our models, and the thing you'll notice that it will start executing on two processors, because it's we can run things in parallel, and you can notice that immediately the harmonic solver is already completed. The transient solver is still running. Now the nice thing is we can already look at the results of our harmonic solution. So let's do that and wait for the transient solver to. So this is typical how you would look at the results. You have a slider bar here, which you can select which harmonic you want to see. There are some data sets on the right here, and you can also double click on any pipeline to pull up a 2D graph. So here you can see the pulsations in the system. That's the blue line at the different harmonics. So the 5 Hz is the first harmonic, 10 Hz second, and also the allowable. So this is automatically being done generated by BOSpulse based on your line pressure and your compressor settings. And then you can also look at the force. So that's a new thing. It automatically calculates the allowable shaking force based on your piping stiffness. You can supply that. It uses something default if you do not supply anything. That's all automatic evaluation of the shaking forces and your pulsations in your system. So in the meanwhile, you can see the transient solver also finished up. And we can also look at those results now. So it's similar, you can plot those as well. Maybe an important thing to notice is that because the harmonic solver is based on some assumption of linearizing the pulsations, So there will be a slight difference between those two. So if I put those next to each other, on the left I have my transient solver, and on my right I have my harmonic. You can see that the height of those pulsations are slightly off. In this case, the forces. And we definitely recommend that you use the harmonic solver only for design purposes, where you can look at different changes in your system. So if you want to change the resonance length in your system, you can use that to quickly evaluate whether you move your acoustic resonance to a different location, whether you add some dampening to your, so the magnitude also changes in a different ways. And then finally do a run in a transient with the transient solver to evaluate the correctness of your solution. So in this case, the transient solver ran a little bit longer. Maybe it took a minute. Harmonic solver only took almost 1 second, maybe even less. So yeah, the difference is not really shown yet. So another thing we can do is we can set up a parameter study. And we can sweep, for example, our frequency. So now we analyzed our system only at the 5 Hertz, as if our compressor was only running at 5 Hertz. But what we can do is we can add a parameter here. And what we can do now is we can do a series of runs and changing the value of this parameter to look at the influence of, for example, if you run your compressor at a little bit different speed. It also captures the effect of, for example, this changing the speed of sound. There's also a little bit of effect. Go to here, parameter study. Let's say we look at 50 different variation. Start at 4 Hertz and end at 6 Hertz. So now it will take it'll do 50 different runs and change the frequency between the 4 and 6 Hertz of the. So now, if I run it again, so now I have a new case, harmonic parameter it's called. The other scenarios are up to date. It will start on 6 cores and it's done in 6.2 seconds. So still really fast. The transient solver, however, and then I'm going to open up those results now because it takes a long time. I already ran these cases beforehand. So I have a transient parameter here. It's the same one as the harmonic parameter with the transient solver. It took 45 minutes to run. So here you can see that if you want to look at design purposes, there's multiple variations of your frequency. It can be very beneficial to use the harmonic solver to quickly evaluate some changes, and then finally only use the transient solver for final evaluation. And here you can probably also see a little bit better the difference between the two solvers. So if we, for example, if we zoom in at the lower half, so on the left we have our harmonic solver, and on the right we have our transient solver. The acoustic resonance is always predicted at the same frequency. It's just the magnitude that can be off. So if we used the harmonic solver initially, we could already see at which frequencies our system would be vulnerable for acoustic resonance. So we could design for that. And then the transient solver would determine the exact magnitude. You can see for some peaks there, the magnitude is definitely off. For others, they're relatively close. And so you can clearly see, for example, for this sweep, you can see the different peaks, and the same thing for the harmonic solver. You can see the same peaks. So now I'll show you a little bit about how you can show your results. So this is a new feature, it's the custom reports. Here you can select what you want to show. So we're going to see relative pulsations. There are other things you can customize. Select which scenario you want to show, which harmonics you want to show, and then I think this is the nicest part, is to show the maximum over either your variation or your harmonics or your elements or all of them. So I'm going to say I want a maximum over my variation. That's a variation of frequency from 4 to 6 Hertz, and to show the maximum over the selected harmonics, so from 1 to 20. And I can go to generate, and here's my list then. It shows me for each element, it shows me the maximum relative pulsation. It shows me at which harmonic, at which variation. So this is a relatively small table, but if you don't take the maximum over the harmonics, for example, this table becomes a lot larger. Another thing regarding the API analysis is you have the standard report, so you can go to select this one, the API 618 Pulsation Compliance Report, and this gives you an overview of all the different system checks that have been conducted and whether the system passed or failed. So right now it says failed. At the top here it says some shaking forces were exceeded, some pressure pulsations were exceeded, and then you can look them up later further in the report. Another thing that's interesting is you say here that's the maximum allowable peak-to-peak pulsation for the compressor cylinder flange. That's something we didn't put in yet. I'll show you that. That's a new feature. Also, the pressure drop over the pulsation device, that's included now. We didn't set that up yet. And then also the shaking force on the pressure suppression device is also not set up. But those checks are included. So I'm going to show you right now. There's a new feature how to set that up. So let's look at the compressor flange first. It should be somewhere in between here. So we can simply split this element. Now we have two elements, and let's say the compressor flange is going to be in the center of that. So we can go add a node here, select that node, and simple is the standard node type, and we can change that to a compressor flange. What we need to do now is specify either the compressor node or the compression ratio. We'll specify the compressor node 930, and this will just take the relevant values of the compressor boundary condition to compute the allowable at the compressor flange. Another thing that might be interesting is that this element is probably geometrically correct, but acoustically the length would be smaller because the wave would only be in between the shell of the vessel and the flange. So you can change that by changing the acoustic length. Normally it's equal to the element length, but we can change it to, for example, it's a better approximation of the system real length. So that's regarding the compressor flange. Now we have also have the shaking force, pressure drop, and pulsation check for the pressure suppression device. That's basically our pulsation bottle. So we can do that by selecting the bottle and change the element type to PSD. To a pressure. We need to give it an identifier. This element is also included in the PSD evaluation, so we'll also change that too. That's relatively simple. The final thing we need to do is to set up an analysis, set up our PSD. So we'll say we want to look at PSD1, that's the one we just created. We need to specify compressor node. So we can get the compressor ratio. We don't need to add that right now. We could give a minimum stiffness, but we're not going to do that right now. It takes the minimum stiffness recommended by the API, but you could also add this manually for calculation of the allowable force. There's a moisture separation checkbox here, but most interesting is pressure drop, for example. You need to specify your first node, so your inlet, which is the 900, or actually just the outlet, and then the other one is 950. Now it will look at the pressure difference between those nodes, and it will use that to evaluate the pressure drop over your PSD device. Finally, we add a force calculation, and we need to supply the node and the area, the effective area at which the pressure will be acting. And if you're familiar with shaking forces, this should be familiar as well, that you always have some area where the pressure thrust will act on. And between two elbow pairs, for example, you have a shaking force. So in your bottle, if you're changing diameter, you will also have shaking force. So this is the one side of our pulsation bottle, and then we have our outlet. It's a little bit of a smaller area, and that's because there's still a pipe going through, exiting. And finally, this is the bend node at the other end, a relatively small area. The sum of these areas is always 0. So all we can do now is run our analysis. I will not run the transient parameter because that one took a very long time to determine. But you can already see that the harmonic and the harmonic parameter even is already finished, and it's only running the transient solution of the single case. But let's just go to the reports already. If you go to the API report right now, you can see it did an evaluation of the peak-to-peak pulsation at the cylinder flange. The results are here. It also did a static pressure drop, and it looked at the shaking forces on the PSD device. So those are all new evaluations we've added, and that basically gives you that includes all the API 618 checks for design approach 3 without the full mechanical analysis. So this is as far as we can go with the Pulsation software without becoming a mechanical analysis package. However, if you want to do a mechanical analysis, you can export these forces to Seizure2. And you can even export this whole model. So let's say you created this model initially in BOSpulse and you want to do a mechanical study in Seizure2. You could simply export this model to a Seizure2. And you do that by export through a Seizure2 neutral file. So let's do it right now. We export it as a Seizure2 neutral file. You can select the different file versions. File version 9.0 is added in a new release. So if you use the latest version of Seizure2, you can also do that. For now, we use 8.0. We can go to Caesar, and we can simply convert a neutral file to a Caesar file. And then we can open our model. So as you can see right here, this is our complete BOSpulse model, but now in Seizure2. It didn't take the bands nicely. I believe I selected the wrong one. This is the right one. So here you can see our complete model in Seizure2 with all the correct, with all the correct node numbers, and that's very, very important if you want to do a mechanical analysis. You want to make sure that your BOSpulse results match up with node numbers with your Seizure2 model. So this is a very similar definition that we use in BOSpulse, where you just have an element and you have a from and to node. This needs a little bit of tinkering regarding the mechanical aspect. You need to add some supports. So that's what I did already beforehand. So you end up with something like this. We have a well-supported, this is the cooler, well-supported system. And all we need to do now is export our forces from BOSpulse. So we can go to the results, export forces. You can select the different harmonics you want to look at, the different scenarios. So we're just going to export the second harmonic for this example. And we say where we want to export it to. And that was all it did was create a text file which we can use. I'm going to pull it up right now. a text file you can use to set up an harmonic analysis in Seizure 2. So this is a text file in front of you right now. It's a force with a direction, with a phase, and a node at which the force should apply. That's all automatically generated. All we need to do now is go to Seizure 2. We need to do a static run, and we can set up our dynamic analysis afterwards. Let's wait for the static analysis to finish. And now we can set up the dynamic analysis. And we need to make sure that we select the harmonic. So because it's a pulsation type of analysis, the harmonic solver is very suitable to do this type of analysis very fast as well. Then we add some the frequencies at which we want to analyze it. Let's say from 4 to 6 again, similar to what we did in BOSpulse itself. And then this is the most interesting. You can add some additional rows. And then we can simply copy and paste the values from the text file into Seizure 2. And that's the whole setup. If you have the same node numbering, the same orientation of the elements in both your BOSpulse and Seizure 2 model, this is all it takes to set up your mechanical analysis. So we set the final control parameter of our restraint summary, and then we can run our harmonic solver. So dynamic analysis is running right now. It's on the other screen. And here you can see the results. We did only a couple cases. Let's look at a little bit of an animation. And here, for example, you can see the results of our mechanical analysis. You can see some of the parts are will be vibrating could be vibrating at a frequency of 4 Hz, for example. And so this is typically how you can do mechanical analysis relatively fast based on your BOSpulse results. I think that was it regarding all our new features and the general overview of our different of how BOSpulse works. So there are some links here, and I'll give the word back to Luc Henner right now.
Okay, thank you very much, Wijnand, for that nice presentation. A lot of details regarding the ways BOSpulse can be used and what for types for analysis it can be used. Now, we already received a couple of questions. Thank you for submitting them. In the meantime, if any of you would like to ask some additional questions, feel free to ask them in the GoToWebinar display. There's a questions tab for that. But before we go to the questions, I would like to highlight our conference, which is coming up, which is the 4th conference on flow problems in the oil and gas industry. This will take place in Delft on the 4th of October. And I'll just open the agenda. So at the start of the day, especially if you're interested in these types of software or these types of dynamic assessments of transients in piping, feel free to join us during the morning because we'll have some hands-on training sessions of these software. And then later during the afternoon, we will have several presentations, amongst others, Professor Ruud Henkes from Shell Delft will talk about simulation requirements for oil and gas transport in pipeline systems. And right after that, Dr. Eugene de Villiers from Engis in the UK about efficient industrial conjugate heat transfer in helix. So as mentioned, the location is in Delft, and feel free to register or today. Having said that, I would like to go back to Wijnand and ask him a couple of questions we received. So Wijnand, I just selected a few of them. So the first question is, to which extent do you need to prepare the PCF files, if at all? And he also asks, can any PCF file be used? What is the maximum amount of PCFs that can be used? Can you maybe detail that a little bit?
Yeah, so regarding the maximum number of PCFs, there's really no maximum. So we've done the import function with 1,000 isometrics, and that's really not an issue. It's very well streamed, so it doesn't take 1,000 isometrics doesn't even take 30 seconds to import. So that's very nice. There's no limitation on that. Things you need to keep track of, that all the information you need for your pulsation or search analysis should be there. So, for example, the right pipe schedule. If you don't add that, it will just use the default one. Different valve elements. If you want to include that in your system, you need to add those. And of course, if you have, for example, if you don't have an isometric of your cooler, which might very well be the case, then you need to still add that manually. And the most important thing I noticed when we were importing those 1,000 isometrics, make sure that that all the isometrics are there and that they're somewhat well connected. And so it's okay if there's a little bit of an offset in the global coordinates between two isometrics. The solver or the routine can fix that. But if you really do not have an isometrics, there will be holes in your system, and that, especially if you have a lot of isometrics, that might be difficult to find out after you import it. But even with 1,000 isometrics and you miss a couple and they don't connect that well, it still saves a lot of time. Yeah, to model it, because modeling 1,000 isometrics by hand is it's going to take you weeks, and it took us around a week to import them. So I think it's a very nice feature. I hope that answered your question.
All right, thank you very much, Wijnand. I mean, if there are any follow-up questions regarding this answer, just feel free to provide them. For now, I'll go to the next question we received, and that is a more general question. When working with piping system or designing a new piping system, when do you typically need to perform a pulsation analysis?
Well, the opinions about this one really change. We believe that well, the API 618 for compressors gives you some guidelines regarding this. It's always good to do a pre-study. So to look at your compressor together with your pulsation bottle, to look at the effectiveness of this pulsation bottle to dampen the pulsations of your specific compressor. And you can do this relatively soon in your design. You only need to know the compressor and the pulsation bottle, and not the exact piping. And that's where the most difficult aspect comes into play, is that you need to know the routing of your piping and relatively precise to do these type of calculations, especially regarding the shaking forces and the mechanical analysis. You really want to know whether there are expansion loops, how it's supported, and stuff like that. So I think it's always good to start as soon as possible. But if you start too soon, you might run into a problem where you have to redo part of the work. So definitely do a pre-study, and then as soon as you think the piping routing is almost finalized, you can do a pulsation analysis.
All right, thank you very much again, Wijnand. Maybe it's useful to add that at least a few of the projects for which we've used BOSpulse in the past are also projects related to existing systems, right? If a customer or a operator or an owner has a system that is prone to pulsations and vibrations, it is very useful to have a close look at the system and then see what causes this and how this can be avoided, either way with supporting or maybe something else. That leads me to the third question, Wijnand. The question is, what are often good options to solve shaking of piping resulting from such pressure pulsations? Which parameters of the compressor might be changed to avoid high peaks in the first place? Can you maybe detail this a little bit?
This is a very good question, and I think there are a lot of answers, but I'll try to take you a little bit through the workflow. So vibrations that are caused most often initially by acoustic resonance. So if there's a wave standing in your system which is exactly excited, so you can change the RPM for your compressor, for example. But even if the gas properties change a little bit, you can already move away from the acoustical resonance and the shaking will become less. But most often, only the changing of the RPM will resolve in that case, if you already have built the system. Regarding pulsations, you can also place an orifice at some location. It does increase the power of your compressor, but if you place it at the correct location, you can effectively break that acoustic mode and reduce the initial shaking forces to start with. And then another approach is to solve it mechanically. So you say, okay, we have those shaking forces, but we're going to restrain the pipe well enough that the shaking forces do not cause any vibrations. That most often means you need to supply some actual stop inside the line that's vibrating, stiffen up your supporting underneath that support. That's also often an issue, especially with higher piping. If you only have a T-post and you try to actually restrain the pipe on a T-post, it's very prone to vibrating because the T-post is not stiff. So some triangulation in some cases is even enough to reduce those vibrations. So a lot of different options, and it really depends on at what stage in the design you are and what options are available, also regarding costs.
Okay, thank you very much, Wijnand. This was also the final question, the last question that I would like to ask. So for now, I'm going to end the webinar. Thank you all for joining, and hope to see you during our next webinars. Thank you very much.